Hi, my name is Easton Hitchens, and today I'll be discussing the importance and history of carbon dating. Some topics I'll be touching upon today is a general description of carbon dating, the history of carbon dating, some key developments that have been made, some future developments that are currently in the works, roles of other fields, and some potential and negative outcomes. So I chose carbon dating because carbon dating ties into my degree and could possibly tie into my career. Because as a geology major, geologists use the carbon dating method as a way to give ages to different earth formations and different formations found out in nature, where we can understand when they were formed, how they were formed, and their impact on the environment. Why you should care about carbon dating is because it gives us a better understanding of our history and it can affect our view on the world. One of the key components of history is dates, and understanding when certain events happen can help us better understand how they affected our course of history and have ultimately led to where we are today. So carbon dating is the process of determining the age of organic materials such as fossils and bones. In this method, we use the carbon-14 isotope to date because it has a constant decay of approximately 4,730 years with a plus or minus 40 area of error, and that is known as the half-life, according to Lavarge's article, Biomass Carbon Dating. The amount of carbon-14 in different specimens can tell us some different things about that specimen, such as its environment, its atmosphere, and how the atmosphere ultimately affected it and its environment and its way of life. Here we have a periodic table of elements from the Great Courses Daily's website, Building the Periodic Table. And as you see with carbon-6, it forms some isotopes, and those isotopes are carbon-12 and carbon-13, which are both stable, and carbon-14, which is unstable. They all have the 6 protons, but what makes them different is that they have different amounts of neutrons. Carbon-12 has 6 neutrons, carbon-13 has 7, and carbon-14 has 8 neutrons. With this carbon-14, with it having that 8 neutrons, that causes it to be radioactive and it causes it to decay. So the history of carbon dating is, it was discovered by Willard Libby in 1940. That's based on Aaron Blakemore's article, Radiocarbon Helps Us Date Ancient Objects, but it's not perfect. He discovered that the reaction of carbon is to be 14 carbon goes to 14 nitrogen plus a beta particle. A beta particle is just a negatively charged electron, and which we learned in our chemistry lecture. A beta particle is that negatively charged, an alpha particle is a positively charged particle, and then we have a gamma ray, which is just a high energy light source. He received a Nobel Peace Prize in 1960 for the discovery of the method, and that's from Higgins' article, The Method. Here we have a carbon-14 decay chart. As we can see, we start with 100% of carbon-14, and as we go down through the half-lives, we ultimately end up to, after about 57,000 years, there's only about 0.1% of the original amount. See, a half-life is taking the initial amount of carbon, and through its half-life, at the end of it, we only have half of what's left. And then another half-life, we take half of what is left from the first half-life. And that's how it decays over those 5,730 year plus or minus 40 increments to get to where it goes to nitrogen 14 plus a beta particle. And that's from the Global Monitoring Laboratory's article, Global Monitoring Laboratory Carbon Cycle Greenhouse Gases. Some 2 key developments that have been made is liquid scintillation and the accelerator mass spectrometry, according to Higgins' article, The Method. Liquid scintillation counting is where they convert carbon to a CO2 gas that is being measured in gas proportional counters. It was discovered that certain organic materials fluoresce when exposed to ionizing radiation. And this fluorescence is proportional to the radioactive decay and proportional to the amount of carbon-14 present. So we were able to see what color it fluoresces to understand how much carbon-14 is present and how long it's been decaying. And that's from Hogg's article, Liquid Scintillation Counting. Here we have an example of a liquid scintillation counter where we can see the beta particles are emitted, which causes the solvent and molecules to be excited. And in the next image, we can see where they're fluorescing different colors, which shows us how much carbon-14 is present and directly how long it has been decaying. And this image is from Perkin-Elmer's website, Liquid Scintillation Counting, LSC analysis. Another key development is the accelerator mass spectrometry, AMS. Here we take radiocarbon and convert it into a solid graphite form, where it is then hit with a cesium gun, where it produces negatively ionized carbon atoms, where they are then moved to a stripper, where they lose these electrons and become triple positively charged atoms, and the quantity of the carbon-14, carbon-13, and carbon-12 can be gathered. And that's all from the Beta Analytical Testing Laboratories article, Accelerator Mass Spectrometry, Carbon-14 Dating, What is AMS? Here we have an example of an accelerator mass spectrometry from Purdue University, What is AMS? And here at the ion source, this is where the specimen is hit with that cesium gun, where it becomes the negatively charged ion. They are then moved to this injector magnet, where the magnet bends them at a 90-degree angle, where it then is able to see the masses of these specimens from their bend, because carbon-12, carbon-13, carbon-14 have a different bend. It is able to take this information and take the specified mass that we're looking for and put it into a specimen container, where it is then moved down to the tandem accelerator. Here, it is accelerated towards a positively charged pool within it, where when it gets there, it's passed through a stripper. This is where it loses those electrons and becomes triple positively charged. When it becomes triple positively charged, it is then repelled from this terminal and sent towards the ground end, where it is then accelerated again at a percent of light speed at about 50 million miles per hour. After this, it's sent to an analyzing magnet and a switching magnet, where the selected mass of the radioisotope and reduces the intensity of the stable isotopes around it, so we can better see which isotopes we're looking for and be able to sort them out so we can count them. It is then sent down to the electrostatic analyzer, where here again it bends the beams to the left by 20 degrees, so we can select the particles based on their energy and sort them out from particles that received wrong energy from the accelerator. It is then sent to the gas ionization detector, where they are slowed down and ultimately brought to a halt, where it counts the ions one at a time, so in red by a computer, so we can determine the rate of energy loss and distinguish the interfering isobars, which lets us count those carbon-14, carbon-13, and carbon-12 that came through. So comparing liquid scintillation counting and accelerator mass spectrometry, it was stated in the Beta Analytical Testing Laboratories article, Accelerator Mass Spectrometry, that liquid scintillation counting is less accurate and less precise than accelerator mass spectrometry, and it takes longer, with liquid scintillation counting taking approximately 1 to 2 days and accelerator mass spectrometry taking only about a few hours. Some future developments that are currently in the work for the method is that there's a team of scientists from the University of Arizona which are looking to remodel the calibration method that ties with carbon dating. They're looking at the way that spikes in carbon in the atmosphere can directly affect calibration curves and able to give more accurate dates to specimens. That's from Litvak's article, Radiocarbon Dating Gets a Postmodern Makeover. See, what they do is that they take these specimens, and they put them in a tree ring model, where they take the tree rings and they count the average amount of carbon present in each tree ring, and take this average amount and put it on a diagram, on a point on a diagram. They then use this to give a relative age of the specimen. See, what they're looking for is how the spikes of carbon over that specimen's lifetime directly affects our ability to accurately date it. See, what they're wanting to do is get it down to where we don't have as large of an area of error, so we can limit that plus or minus 40-year area of error. Chemists play a role in the method, and the fact that they actually are the ones who discovered the method. Willard Libby, who discovered the method, was a chemist. Chemists don't actually use it on a day-to-day basis in their career, but they study it and adjust it when new discoveries are made to help us give a better accurate date for the specimens that we're dating. And that's from Higham's article, The Method. Other scientists play a role in carbon dating is geologists, paleontologists, and archaeologists use the method the most, based on Aaron Blakemore's article, Radiocarbon Helps Us Date Ancient Objects, but it's not perfect. They use the method to date specimens that are closely related to their area of profession. Geologists use it, like I said, to give ages to earth formations out in different environments and how their impact has affected their environment. Paleontologists use it to give ages to different organic materials that they unearth, such as fossils and bones and stuff like that. And archaeologists use it to give ages to different materials that they have unearthed at archaeological digs. The role of law in carbon dating is that we are currently pumping carbon into the atmosphere at an alarming rate, and this can directly affect our ability to accurately use the method to give accurate dates to different specimens. Right now, there are greenhouse emission standards in place to help limit this amount of carbon in the atmosphere. Phase 1 was between 2012 and 2016, and we are currently in Phase 2, which is going from 2017 to 2025, and that's from the United States Environmental Protection Agency article, Regulations for Greenhouse Gas Emissions from Passenger Cars and Trucks. These laws help us slow down the amount of carbon that we are pumping into the atmosphere so we can protect our environments and protect our way of life. But it also helps us protect specimens that we're trying to accurately date and give accurate ages to them so we can better understand how they lived, when they lived, and what their environment was like when they lived. So potential positive societal impacts is that carbon dating can help us understand how the world has evolved. It helps us understand how environmental changes affect life sources. It helps us understand how past humans have lived. And it gives us a better understanding of how certain events in history have directly impacted our environment. And that's from Litvak's article, Radiocarbon Dating Gets a Postmodern Makeover. See, it helps us understand how past events in our history has ultimately led up to where we are today. And with this better understanding, we can understand how actions that we take today will affect us tomorrow. We can understand how the actions of past humans negatively impacted them, so we can learn not to make those same mistakes in the future to help us protect our way of life and our standard of living.